So let's talk about the effaceability of a delta functor. There is an important theorem, authentic in his Tohoku paper, stating that a delta functor plus effaceability of this delta functor implies universal delta functor. We'll give a sketching proof, but let's start with the definition part of the terminology. So firstly, a delta functor or a comodular delta functor between two abelian categories A, B is defined to be the following data. Firstly, it is a collection of additive functors Fn for each n non-negative integer. Secondly, it is a collection, there is also a collection of connecting morphisms. This is the same phenomenon as in the homology of chain complex. We have given a short exact sequence, you have long exact sequence, and the jumping degree arrow is called connecting morphism, whose existence, if you think about the proof in that case, comes from the snake lemma. Okay, it's the same connecting morphism, we use delta actually. So these two data satisfy the following theorem. Firstly, short exact sequence goes to long exact sequence with this connecting morphism delta. Secondly, kind of the how to say I should not say naturality actually. It's just a condition of the commutative of this delta functor. Basically, what does this mean? Mean that fi, they are all functors. And so if you have short exact sequence 0, A, B, C, 0, and you then apply a functor f to it, just by the definition of a functor, it have to commute with the composition. This already implies that if you have commutative diagram, you then again have a commutative diagram, because this is just composition of under a functor is a composition of its image. But this cannot tell us this diagram is commutative or not. That's kind of the relation between f0 and f1, right? It seems like not really like the naturality. Okay, just think of it as part of this definition, in my opinion. It's not something like natural transformation of functor f0 and f1, because if that is the case, if you require something to be natural transformation, then for whatever say to A, you have to check the diagram. What you really have to check is for morphism is abelian category A. Okay, if you say C to C prime, then you have to apply both sides C to C prime. This is not the case. Okay. Okay, this is the definition part of this delta functor. So if you feel this is strange to remember, I would say just remember that for short exact sequence, you always have a long exact sequence commutative diagram. That's what I would say. And then what is called universal delta functor is a delta functor satisfies universal property, which is given another delta functor g, and a natural transformation on the degree 0 of their functor, ideal functor f0 to g0. It extends uniquely to a morphism of delta functor. So what is a morphism of delta functors? This is actually something very important to remember before we proceed. There are two parts. Firstly, of course, it is natural transformation functors in each level. Okay, so each Tn, degree n level, it is a natural transformation. Secondly, again, there is a condition on the commutative diagram. So you have, basically, I would still suggest if you have shortly that sequence 0 to a to b to c, then the corresponding long exact sequence still commutative diagram. So those parts are directly from the fact of natural transformation, but the connecting part is not obvious. Okay, that's why we require it. So there are two conditions. The statement of this result is that if you have AB abelian categories, a delta functor f, and if it is effaceable delta functor, or we say delta functor satisfies effaceability, has effaceability, which means that in your category, abelian category A, for whatever object big A, let's say there exists an injective map from A to B in category A such that all the fi is the collection of your data functor. Applying on this embedding map U is a 0 map. This expands effaceability. We don't require F0. We don't require F0. This is for fi bigger than 0. Okay, then this is called universal delta functor. Then this is called effaceable functor. The result is this plus delta functor implies universal, which means that, let's say the proof, which means that for any given delta functor g, still from A to B, whose T0 coincide with your f, whose T0 is given, then it can extend uniquely to Ti for I bigger than 0. This Ti, it's not arbitrary map, but it's morphism of delta functor, which means those Ti have to be natural transformation themselves. And secondly, you have to satisfy this commutative diagram condition. That's what we have to check. We didn't. So this proof here is from stack project. It just explains how to construct that map Tn. Basically, it just tells you how to construct that as map of those. Construct a map Tn from Fn to Gn. But there are two things still left to check. First, the naturality. Secondly, the commutative diagram, which can be seen from the definition of morphism delta functors. Okay, so let's first see construction. Construction is just apply your delta functor f to the short exact sequence 0 to a to b to c to 0. What you got is you got a long exact sequence by the definition of your delta functor. And this long exact sequence, if you look precisely, tells you f1u is 0, f2u is 0, etc. Split this long exact sequence into short exact sequences. Basically, for I bigger than 0, you will got this short exact sequence, which tells you that fn plus 1a is actually the co-kernel of fnb to fnc. And then because fn1a is now co-kernel, you could use universal property. So let's look at this diagram here. You have this unique morphism from fn plus 1a to gn plus 1a because your fn plus 1a is co-kernel of f1b to fnc. You don't know your gn plus 1 is or not because g is not effaceable, but f is effaceable. Delta functor implies that fn plus 1a could be regarded as co-kernel. So we are using actually induction, right? We're using induction. We suppose all those Tn are already in natural transformation. So they are all commutative diagrams, for example, the square here. And so this would tell you that you have unique morphism by the universal property of co-kernel, because if you go this way, it's the same as you go this way, give you 0. And so universal property tells you there is a unique map from Fn plus 1 into Gn plus 1. This is our definition with Tn plus 1, but still left to check natural nullity and commutative diagram. So let's look at some question asking method of flow or mass stack exchange. So this question put here exactly ask for the left part. So the construction here are the same. The final question is there are two things left to check. Firstly, the natural nullity. Secondly, natural transformation Fn commutes with connecting morphism. So the proof is that you embed to check the natural nullity, you embed an arbitrary map in your category A, phi B into the level, into the effacement, into the effacement injection map, which is the one we called U before. So A embedded into MA, B embedded into MB. MA is the effacement embedding of A, and B is the effacement embedding of B. So small trick tell you that you can make it such that MA to MB is a map which extends this frobenius, which means we embed this morphism of A2B to a morphism in the level of effacement embedding. Okay, and then you fulfill this into short exact sequence, map it to its co-kernels. And then what we do is, now let's look at commutative diagrams. Comes from firstly, so for example, look at here, you just apply your delta functor f by the long exact sequence, you got this. Similarly here, by long exact sequence 2b, you got this. All the diagram here are commutative. This just comes from the fact that f is a functor, as we said, but here comes the fact it's a delta functor. By definition of delta functor, it has commutative with delta connecting morphisms. Okay. Similarly, in the part of G, you got all those vertical squares commutative because it's delta functor. Again, with nothing more than that. And then those horizontal squares, they are commutative by induction. This is, for example, this one. It's just because T0 is natural transformation. We suppose, so in induction, you have to show that T1 is a natural transformation, which is left to show this diagram is commutative. Okay, you have to show this diagram is commutative. How do we show that? Actually, realize this could be induced from the commutativity of the above diagrams. So the above diagrams are already commutative. Yeah, one more thing to say, actually, yeah, I forgot, is you have to notice this diagram is also commutative, this one. This is also a commutative diagram. Okay, why? All the, and also, let me see, also this one. I'm not going to mention all of them. Okay, so why this is the case? This comes from the fact you already have T0 given. T0 given as natural transformation, right? This comes from natural transformation. Wow, this one actually comes from our construction of T n plus 1. It is commutative by our construction just mentioned in the first proof. I mean, here, okay, or you see here. By our construction, this is commutative. So what is left to show is what I mentioned. Is this commutative? So we haven't used the fact f is effaceable, so that will tell you that this is a zero map. This is f1u because for u, I mean this is u, ua, for example. This is f1ua. And so there is this trajectory map, you can find a prime which map to this. And then this diagram is commutative, tells you that the following one should be, because it's just this one, and because all the side circles are commutative, you just translate just commutative diagram into the commutative diagram, the lower one, because the question is A map to B and B map to TP1B, and then A map to TA1A. The question, for example, you can ask, is this the same? But then this comes from the fact that this map to this and this map to this also map to this, and then this map to this. And so this commutative diagram will tell you that this one must be the same as this one. Right. Okay, so it's back here. So this tells how to deal with the natural nullity. And then one more question is about this commutativity with delta connecting morphism. Put it more precise, the question is here. So for any short exact sequence 0 to A to B to C0 in your category A, do you have a commutative diagram with connecting morphisms? What you do know is in the level of effacement embeddings, which is here, by our construction, you already have this commutative diagram with connecting morphisms. This is our Tn mentioned before. Here it's called Fn just. Okay, what you don't know is in the level of general morphism. But what do we do? You can still argue with embedding of that complex into short exact sequence into short exact sequence in the effacement level, which means if you have 0 to A to B to C, then you could embed B into one with effaceable injection, and then you just fulfill this into diagram. And then, as you could imagine, we could do something very similar to form something cubic diagram if you want, and to say that actually a commutative diagram it could comes from the level of effacement. Okay. Anything more to mention? Yeah, you could still ask why the fact that we're constructing these maps from a particular embedding doesn't depend on this particular embedding, right? This is also asked by another question in math stack project, I think. So the answer is, suppose you have two different effacement embedding, A to M and A to N. You can actually embed both of them to even bigger effacement embedding and plus N under certain precise construction omega, which in this answer is I just use IM compose U plus IN compose V. The fact is that when you embed an object in its effacement embedding, your induced homomorphism doesn't change, right? What you have to check is that, for example, if you see it doesn't change, then you will see that the one embedded, the one induced by this embedding and the one induced by this embedding coincide with the one induced by this bigger embedding. And so the embeddings are independent of the choice of your particular embedding, right? Okay, so let's say y a embedding to m is the same as a embedding to m plus n. Suppose you have your embedding, effacement embedding here, and then you have even bigger effacement embedding here. We just want to show that they finally induce you the same what? The same map delta 1, right? And by induction, it works for the data n once you know delta n minus 1. So the argument is you look at this commutative diagram, and then you apply your delta functor t and apply your delta functor g. So in this answer, he write the delta functor g. So we were considering t to g, right? He's writing t to t bar. It's just notation. So in his notation, we will write this. This first arrow is nothing but the line exact sequence of t. This is line exact sequence of g. Again, line exact sequence of t, line exact sequence of g. This is for the first arrow. And this is for the first arrow, sorry. And for the second arrow here. Okay. And then again, you have a commutative diagram. This commutative diagram tells you that just by induction, you will see that all those are commutative, right? Basically, what I want to say that I'm still having it makes it very strange. It's still a square actually. Okay, let me just avoid writing this. So what you have to check is that this is the F1 or our T1 induced by the first effacement embedding. This is the one induced by our second embedding. You'll just have to see they give you the same map. Actually, they are both as a module. They are the same. They have the co-kernel because they are both isomorphic to. They are both T1A. They are identically, but the one is regarded as co-kernel of this map. The other is regarded as co-kernel of this map. We just want to say that because we are constructing this arrow using the universal property of co-kernel, we just want to say that as co-kernel of this and as co-kernel of this, the induced F is the same, right? Let's call this F1 tilde F1. We just want to compare F1 tilde and F1. We want to say they are the same. So the reason they are the same is because that we want to say that it comes from the fact you have a commutative diagram. So if you start with your object here, and then you map it to here, you want to ask, is it the same as I starting here? And I map it here. Is this the same element? The reason is yes, because it's a commutative diagram. So the element here identically with the element here because you're using identity map here. So there's and the natural transformation this is not even natural transformation, this is just a functor. Let me think. Just a functor applied to identity is identity of, right? So let me write. This is just the identity of FA to FB. This is by definition of a functor. And so this is just identity. So once you know this is commutative diagram, you will know that this is mapped to the same as this. Why this is commutative diagram? Because all the preceding ones are commutative diagram. All the preceding ones, I mean, those are all commutative diagrams. Those are all commutative diagrams. Okay. And it's very similar as diagram I drew before. This commutativity of the first three will imply the commutativity of this one because this is surjective. And so hence we prove this smaller effacement embedding could embed into the bigger effacement embedding, and they give you the same higher degree Tn from lower degree Tn minus 1. This should finish the proof.